AP Chemistry, we're on to the day 57 assignment. This will be the last assignment of this unit. It's on a concept called Le Chatelier's principle. So I start you off with some more ice table problems in this assignment. Number one is a repeat of a problem you had on the last assignment. So see if you can do it. There's the answer right there above the rice table. Go ahead and see if you can do this on your own without reviewing your notes. But if you need to review your notes, go ahead and do that. Okay, so part B of this problem, part B of problem 1, if the concentrations of H2I2 equal 0.20 each and HI is 1.34, compute the value of Q. Will the reaction favor products or reactants? So it should have been clear that those are equilibrium concentrations. So let's go ahead, let's just assume that those are equilibrium concentrations. I'm not going to ask you to set up another ice table. So that means you don't need to set up an ice table. What ice tables are designed to do is get you to the equilibrium concentration. Let's just say these are equilibrium concentrations. So we have the same equation up above, so the rate law for this is going to be, and now substituting these equilibrium values. Okay, and we go ahead and we do the math on that. Okay, and what we get for that is 0.45 for your Q. And this was a mistake to write that as Kc. It's not. We're figuring out a Q value. So again, what is a Q value? It's calculated exactly the same way as an equilibrium constant at K, except it's whatever the existing concentrations are, not the equilibrium concentrations. Okay, so we did that and we came up with this. So up here we have our value for K. So, and Q equals this. So what it means is it's a very small number. That means the reactants on the bottom of the equation dominate over the products on the top. It has too much reactant for the amount of product. So what the equation would like to do is get this mixture up to a equilibrium value of 16, but it's way below that. So if Q is less than 16, it's going to move in the direction of products. It's going to move from right to left. So that means that it's going to favor products. It's going to move from left to right in the direction of products. And so that's your final answer. All right, number 2. Okay, so decomposition reactions, these are equilibrium concentrations, so you already know the equilibriums, you don't need to use the rice table. Okay, so you don't need a rice table if you already have equilibrium concentrations. All right, so there's your equilibrium concentrations, there's the Kc value. It says compute Q and determine whether it favors products or reactants, so you do it exactly the way we did 1B, and I'll leave that for you to do. Okay, continue on with problem 3. Also, consider these to be equilibrium values. So you don't need to have a rice table for this answer. All right, let's move on. All right, problem number 4. It is also a review problem from the previous lesson. Go ahead and see if you can do it without looking back to the day 55, 56 lesson. But if you can't, go ahead and look back there, but you will see the solution in the answers video for day 55 and 56. Okay, number 5, same thing. It was done the solution is in the answers video for day 55, 56. So go ahead and do it here. Again, the idea here, the reason for giving you these problems a second time is to see if you can do them by yourself. But if you can't, check back on the answers. But Eventually you don't know how to do the problem unless you can do it completely on your own without any help. So see if you can do this one like that. The answer is on day 55, 56. Okay, and also problem 6 was done on the day 55, 56. It is in the answers video there, so go ahead and refer to that. See if you can do it on your own. That's the key to doing it a second time. Okay, we're going to move on to problem 7. This wasn't given in the previous assignment. Let's go ahead and do this one together. It consists of a diatomic iodine molecule decomposing into 2 iodine atoms. Now, do you think that wants to happen naturally? Do you think that's going to have a big K value? If you didn't see the K value here, would you expect it to be large or small? Well, the answer is iodine is one of the 7 elemental diatomic molecules. It's just a single element that naturally wants to form a diatomic molecule, I2. That's the way nature has iodine gas, the way it exists. So breaking it apart is not natural. It doesn't naturally want to come apart. So this reaction is going to have a low Kp going from left to right, and in fact it has a pretty low Kp. This number means 2.91 over 10,000. So it's a very small number. Alright, so let's go ahead and do this. So on this side, first of all, we only have one reactant, one product, so we don't need that box. You don't really have to X it out, but you don't need it. Okay, so there's the reaction, and it says initial pressure of I2 is 1. Again, in these problems, I'm going to avoid trailing zeros, although we understand that those are important for significant figure reasons, but I'm going to ignore them at this point. Okay, we're going to assume that we have 0 here to start. Okay, and it wants to know the equilibrium pressure of both of these. So this has a coefficient, the I2 has a coefficient of 1, so the change variable is going to be minus because it's being reduced. This is concentrations being reduced, the product. 1 because it has a 1 in front of the in the equation, and x, which is the change variable. So this on this side is simply going to be 1 minus 1x. I'll simply write that as 1 minus x. Alright, now we come over here, and this is going to be increasing. It's a product. It's going to be going up in value, so it's a plus. The 2 in front of this makes the 2 in front of the change variable, and the change variable x. So now we simply add 0 plus 2x gives you 2x. So now you have your algebraic expressions for your equilibrium concentrations. Now write the law of mass action for this. So I'm going to come way over here. Okay, there it is. So now we can plug in our algebraic expressions here. Come over here and do that. And go ahead and put our actual numeric value of Kp in. Okay. Again, sometimes once I go into the actual algebraic expression, I switch over from square brackets to parentheses. It doesn't really matter. Okay, so let's simplify this a little bit. And on the top, you're going to square this entire expression here. So 2 squared is 4, and x squared is x squared. So that becomes 4x squared without the parentheses. On the bottom, we're going to use the simplifying assumption. Okay, I told you could always do that this class. If you don't, you're going to end up with a quadratic and have to use the quadratic formula. So we're going to assume that x is much smaller than the initial concentration of 1. We're going to say this is much, much smaller. Now we're going to have to test that out at the end of the problem to see if it's true. But for right now, let's go ahead and make that assumption. So that means you can get rid of this x right here. So this simply becomes a 1 over here in the denominator. Alright, so now what you have to do is divide both sides by 4. So I am going to come down here and do that. Cancel on that side. And now we simplify this. And it's 0.72728, I'm going to say. Don't have to worry about adjusting the decimal because you're not at the end of the problem yet. So you leave that kind of thing until the very final answer. Equals x squared. So now I'm going to take the square root. I'm going to move the x over to the left side here and take the square root of x squared and take the square root of this. Okay, and when we do that, we come down here and we get x equals, and we get, I'm going to write it in regular decimal form. Okay, that's the number we get right there. Okay, so we know X. That's not what we're looking for finally. We want to know what the concentration of I2 and 2I is. But before we plug it in, let's do our test to see if it's valid. It has to be less, 0.0085 has to be less than 5% of your initial concentration of 1. So you take the X value, and then you multiply by 100%. That's the initial concentration of 1. Okay, and what we get is so the answer is yes, since this is less than 5%. So yes, the simplifying assumption is valid. So now we're ready to get our final answer by taking X and plugging it back in to get the equilibrium concentration of I2 and then of I. So for I2, it's going to be 1 minus. That gives us this. And it's a concentration, so it's molar. For I, you don't say 2I, it's just the concentration of I. It just happens to be 2I in this particular reaction. So it's... And you notice I am always very cautious. I use my calculator on this calculation, even though I can do it in my head. I want to be sure I don't mess up the zeros, because I do that fairly often. Okay, so it's going to be... And that's molar. And that's the final answer. So these are your two final answers for this problem. Okay, let's go ahead and do 8 together. So that one has not been done on a previous assignment. Again, the purpose of me doing all these problems with you is that you know how to do them and now you go practice them. But you should try to do them on your own first, then see my solution, and then practice them. Okay? You take a piano lesson, and you sit down with the teacher and you stumble your way through a piece of music, and then you go home and don't practice, you're not going to get any better. You've got to practice these just like practicing anything else to get good at it. Okay, let's go on to number 8, and the equilibrium constant for the given reaction is 0.561 at 800 degrees Kelvin. Okay, 0.561. That is not, as equilibrium constants go, that is not a very small number. So let's write a couple of just hard and fast rules, okay? Okay, let's read this together. So if k is less than 10 to the negative third, that would be 10 to the negative fourth, 10 to the negative fifth, 10 to the negative sixth, and so on, then you can use the simplifying assumption. Because your change variable x is going to be very small if k is very small, because not much of your reactant is going to go to product. So it's going to be very small change variable x. If k is greater than 10 to the negative third, so 10 to the negative second, 10 to the negative first, 10 to the second, 10 to the third, so on, in other words, getting bigger, then you cannot use the simplifying assumption. It's too big. This is not a hard and fast rule, but it's a pretty good rule of thumb. All right, so as we read this problem, we see that the equilibrium constant is 0.5. That's going to be 5.61 times 10 to the negative 1. That's a fairly big rate constant. So we can't use the simplifying assumption here. So again, as you just gained experience doing these problems, you'll learn, to make that judgment. Now, if the initial concentration of HI is 0.5 molar, what are the equilibrium concentrations of each species? Okay. By the way, that term species just means the products are reactants. Okay. And sometimes you'll see the term major species, meaning it's in the solution in great numbers, and minor species means it's just little tiny bits of it are in the solution. So major species, minor species, it just refers to products and reactants. Okay, so rather than having to say products and reactants, they just say species. Okay, so let's write down this. Okay, so we have initial concentrations of HI is 0.5. molar. And we're not given initial concentrations for H2 or I2, so again, anytime you're not, if you don't make this assumption, you can't do these problems. You're going to assume it's 0 since they don't give you any. So what we see is the only species that we have in the container is the HI, so that's got to be decreasing. It has a coefficient of 2, so it's going to be decreasing, negative. It's got a coefficient of 2. And then the change variable x. Okay, over here, since this starts off with 0, it has to be increasing. So it's going to be plus, coefficient is 1, and the change variable x. Same here, plus 1x. Okay, so now we go ahead and sum them up for the equilibrium line. So 0 plus 1x, I'll omit the 1, it's just x. Same thing here. And 0.5 minus 2x. Okay, now let's go ahead and write the law of mass action for this. And we're going to call it K. And it could be concentration, it could be pressure. Let's just call it concentration. They say equilibrium. Okay, there you go. There's the law of mass actions. Let's come over here and plug in our algebraic expressions and our equilibrium constant. Switch over to parentheses. Okay. All right. Now, if we can't use the simplifying assumption, this expression right here means we're looking at doing a quadratic formula. But this is in this one unique situation where both of these are the same. Watch what happens. You'll see we've seen this before. So I'm going to come over here. So we're going to keep this as x squared. And now we're going to call this x squared. So we lucked out in a sense. I said you weren't ever going to have to use a quadratic formula. You won't here, although you can't use the simplifying assumption. This is kind of an exception. You have a square over a square, which means you're in luck. You can simply take the square root of this and not have to deal with a quadratic. Okay, so I'm going to come down here and take the square root of this side. Okay, we move over, we take the square root of 0.516. 561 rather, and we get this. And on this side, the square root just does both of these squares, so you end up with this. Okay, so convince yourself that that turns into that. All right, now it's just an algebra problem here. We'll multiply both sides by x. These canceled, of course. Okay, now what we're going to do is add 2x to both sides. This goes away, and then you have 0.5 over here. And that's 2.75x. Okay, now we divide both sides by 2.75. That cancels, and you end up with x equals 0.5 divided by 2.75. And that gives us 0.182. All right. We don't have to test the simplifying assumption because we didn't use it. So now we can take our x and plug it in for each of these to get the equilibrium concentrations of the three species, and that's the final answer. So let's do H2 first. And it's simply x. So the concentration of H2, same for I2. X is simply the concentration of I2. And finally the concentration for HI, don't write 2HI, it's just the concentration of HI. It's going to be this. And that gives us 0.136 molar. So those are your final answers. Those are the final concentrations once this reaction has reached equilibrium at a temperature of 800 degrees. some other temperature, it would be some other values for these because the equilibrium would be in a different place. And that's a concept we're going to get to in the next few questions on Le Chatelier's principle. So let's go ahead and do that. Okay, let's work through these together. So determine whether reactants or products will be favored. Again, reactants being favored means the reaction moves backwards from products back to reactants. Products being favored means it moves forwards from reactants over to products, from left to right. All right, so here's just a generic equation. It's exothermic. Now, we're not calculating delta H's here. We're calculating the movement of the reaction. But this is something you need to know, that if it's exothermic, it means heat is treated like a product. It's coming out of the product side. So it's coming off into the atmosphere, for example. And so there's a number for it. All right. So the concentration of A is increased. That's right here. So I want you to write out these explanations. I'm going to give you we're going to work most of them together. I'll give you a few to leave on your own. All right. So the concentration of A is increased. So I'd like you to write this out. Okay, so then when A is increased, the left side of the reaction, this side over here, becomes more crowded. That's kind of just a metaphor. It's the crowded room idea. And so the reaction's going to move to the right, okay? The RxN means reaction, okay? So for this one, if you want, you can draw an arrow right above it like that, or right out here, you can do that. Okay? Concentration of C is increased. So over here, and I'll write in kind of a shorthand now. Okay, if C is increased, the right side, this side over here, becomes more crowded, and the reaction moves backwards. It moves in the reverse direction. Okay, and I should use the term favors. I didn't have room up in the first problem. Favors reactants. Okay, the concentration of D is decreased over here. So what happens is if you decrease either of these two, then this side of the equation becomes less crowded. There's fewer people in the room over here. So the people on this side want to be more comfortable, so they're going to start moving over to the right. Okay, I'll just continue this sentence. Concentration of D is increased. Okay, so you decrease that, this room becomes less crowded, so people over here want to move to the right. So that's going to move to the right, and that's called favoring products. Okay, temperature is increased in the reaction. All right, so this is where the exothermic part comes in. Look at this reaction. When it naturally proceeds, it goes from left to right, and it produces C, D, and heat. Heat comes out of it. Okay. So heat wants to come out into the atmosphere. But if you turn the temperature up, it's harder for heat to move out into a hot room than a cold room. Think about it. If you're sitting next to a heater in a hot room, in a very hot room, and you turn on the heater, you don't even notice that it's on. It's hard for the heat to get out into a hot room because the room is already at a high temperature. If it's a very cold room and you turn on the heater, you feel it quite a bit. You'll notice it right away. It's very easy for heat to get out into a cold room. So if you increase the temperature of the reaction, you're making it harder for the heat to escape, and therefore the reaction doesn't want to move to the right. And in fact, if you turn the heat up high, or the temperature up high enough, it would move backwards. So let's write that out. Okay, so increasing T in an exothermic reaction makes it harder for heat to escape to the surroundings. This pushes the reaction in reverse to favor the reactants. It's going to go backwards. You can kind of almost think of this as the crowded room principle for heat. If there's already a lot of heat in the room and heat is trying to escape out into the room, it's going to say, hey, this room is too crowded with heat. It's got too much heat out here already, so I'm going to go backwards. That reaction's going to go backwards or go in the reverse direction. Okay, so I want you to give a similar explanation. If it's an exothermic reaction, give a similar explanation for if the temperature is decreased. What will happen to that reaction? Okay, let's go on down here. Do a different one. Now, we should also add, since I didn't give you any specific questions, if it's an endothermic reactions, let's just write a simple one here. Okay, endothermic reactions, if this is endothermic, so it has a plus delta H, that means in order for it to move forward, it wants to take in heat. So if you add heat to an endothermic reaction, you're feeding the reaction. You're giving it what it needs to move from left to right. So adding heat to an endothermic reaction, one that naturally wants to take in heat in order to proceed from left to right, is going to make it proceed from left to right better. On the other hand, if you take heat away from a reaction, again, just think of heat as one of the reactants. Heat plus A plus B gives you C. If you take away one of the reactants, then it's not going to move to the right as well, and in fact, if you take enough away, it's going to move back to the left. So that would favor reactants if you take heat away from an endothermic reaction. Okay, so let's go on down here. So determine whether reactants or products will be favored. Okay, so we have a synthesis reaction of NO2 to produce 2N2O, and that has a delta H of negative 58. So again, that's exothermic. All right, so the concentration of NO2 is increased, so you're increasing the concentration of this. The room is becoming more crowded, and so the reaction moves backwards to the left. It moves in the reverse direction. All right, concentration of N2O2 is decreased, so this is decreased. So the room over here becomes less crowded. What's going to happen? Again, give a full sentence explanation, okay? Now, on an AP exam, I would not use a word like crowded. I would use concentrated. But I'm just trying to give you some metaphors to kind of learn how this works, okay? So you can do B. C, concentration of NO2 is increased. You're increasing that. What's going to happen? You can do that one. Concentration of NO2 is decreased. You can do that one. Temperature is increased. Okay, again, it's an exothermic reaction. So the heat is trying to get out. So it's this plus heat. Again, you know it's exothermic because delta H is negative. It's like money in your bank account. Now, negative delta H means it's going out. The heat's going out. So if you turn up the temperature of the room is really crowded with heat already. And so that means it's going to be harder for the heat to escape the reaction. So that's going to push the reaction back to the left. Okay, so write that out. Temperature is decreased. Same thing. Now you've got the heater in a very cold room. You've turned the temperature of the room down very cold. Now the heat's going to be able to get out very easily from that heater into the cold room. You'll really feel the heat coming out of that heater much more if it's a cold room. So it makes it easier for the heat to escape if the room isn't already crowded with heat. And so decreasing the temperature makes the reaction move to the right towards products. Pressure is increased. Okay, let's do these two together. We did not deal with this in the previous problem. So pressure, it's a gas. So if pressure is increased, first of all, let's start with PV equals nRT. If pressure is increased, you make the pressure go up. Then what the reaction wants to do is go against that. It wants to get back to equilibrium. It says, hey, the pressure's too high. I'm not happy anymore. I'm in a room with too much pressure in it. I want to go back. So therefore, what the reaction wants to do is go against that pressure increase. What caused that pressure increase? You might have squeezed down the volume, for example. Okay? And the reaction is saying, wait, I'm under too much pressure for my equilibrium. So the reaction is doing this. It's saying, I want my pressure to go down. So how can it do that? Well, it can't change the volume necessarily or the temperature, but what it can do is change the number of moles. So if the reaction wants its pressure to go down, it wants its number of moles to go down. Okay? So again, the pressure is increased externally from the outside. The reaction is reacting in this fashion. It's saying, I want to go back to a lower pressure because you just increased my pressure. I want to go back to a lower pressure. Therefore, it wants fewer moles. Okay? So it will, the reaction, so let's write that as a complete sentence here. Okay, a little bit of a long answer here. So, pressure was increased externally on the reaction. The reaction's not happy anymore, so it wants to reduce the pressure back down. The one way it can do it is going from the side with higher number of moles by lowering the number of moles. So that means it wants to go from the side that has more moles over to the side that has fewer moles. It can do that. It can reduce the number of moles simply by moving the reaction to the right. Okay? Okay, so this reaction, let me finish the sentence, favors products. Okay? So it's going to favor the products. It's going to want to move from the greater number of moles over to the less number of moles to reduce the pressure. And that's how it goes. So it's not necessarily left to right. It's whichever side has the greater number of moles to the fewer number of moles. That's if the pressure is increased from the outside and the reaction wants to reduce the pressure. So I'm going to leave you to answer what if the pressure is decreased. It's exactly the opposite explanation, and I want you to answer that. Okay? That'll be yours. Okay, number 11, explain briefly how a catalyst affects the rate of a reaction and the equilibrium of a reaction. So that's explained on the very last slide of this lesson. It's not a long slide, but just go ahead. Does it affect the equilibrium? Does it affect the rate? What does a catalyst do? Just a simple couple sentences, 3-sentence explanation, okay? And that'll do it. All right, so that takes care of, for this lesson, the problems I didn't do are generally from the last assignment. I want you to do them a second time and see if you can do them entirely on your own. Okay? If you have any questions, come in for help, and we'll see you on the next lesson.